Section 18, Cosmic Microwave Background, CMB, and Recombination, and Size of the Universe. Now let's cover from 5 minutes after the Big Bang to 400,000 years after the Big Bang, per the following graph. We will learn later that Big Bang nucleosynthesis has completed 5 years after the Big Bang. The density of ordinary matter is less than 10 millionths of the density of water after that time. Expansion of the universe is dominated by radiation energy density in the early millennia, and the scale factor, the blue curve, with scale at the right, is proportional to the square root of time. Increasing time by a factor of 1,000 increases scale factor by a factor of about 32. However, the energy density of radiation is falling faster with scale factor and time than is the energy density of matter. At 50,000 years after the Big Bang, the green vertical line, matter energy density overtakes radiation energy density. At this time, the scale factor is 2.9 by 10 to the minus 4, about 3,500 times smaller than today. Radiation temperature is 9,350 Kelvin versus 2.755 Kelvin today. After this time, the expansion of the universe is dominated by matter energy density, and the scale factor grows with the 2/3 power of time roughly. Increasing time by a factor of 1,000 increases scale factor by a factor of 100. Expansion and deceleration continue. The blue curve curves downward. Radiation temperature, the red curve with scale at the left, is proportional to 1 over the scale factor, so is falling significantly. Something important occurs in the period from 220,000 years to 370,000 years after the Big Bang, during which the radiation temperature falls from 4,000 Kelvin to 3,000 Kelvin. The major constituent of ordinary matter is hydrogen. The hydrogen is a nearly completely ionized plasma, 1 electron separated from 1 proton at the beginning of this period, and nearly completely recombined into a gas of neutral hydrogen atoms at the end of this period, with the cooler temperature. This is called the epoch of recombination. The protons and electrons had never previously been combined as neutral atoms, so we might expect it to be called the epoch of combination, but recombination is cosmologists' name for it. The process of recombination is complicated and interesting, but we will not cover the process. If you take the ionization energy for hydrogen and turn that energy into a temperature, you might think the hydrogen would have recombined at a higher temperature and an earlier time. However, there are about 1.6 billion photons per hydrogen ion, so photons with higher than average energy keep the hydrogen ionized until this epoch. While the hydrogen was ionized, the entire universe was an opaque plasma. Each photon would scatter off free electrons at least every 5,000 years. The universe was opaque to photons. But once almost all of the hydrogen was a gas of neutral atoms, photons were then free to travel the universe without scattering. The universe became transparent to photons. The photon decoupling and last scattering for these photons was at 370,000 years after the Big Bang. The scale factor was 9.1 by 10 to the minus 4, a redshift z of 1089 or 1090. At that time, the entire universe was filled with photons that would look orange or red to us, but so intense that we would be quickly cremated. At the time of last scattering, the energy density of photons was slightly more than the energy density of ordinary baryonic matter, but less than the energy density of dark matter. The hydrogen density at that time was less than the best vacuum ever achieved on Earth. Some authors use the term hot Big Bang to mean the time here of CMB last scattering, the oldest light we can see, and other authors use Big Bang to mean the hot dense state at either the Planck time, which I have used, or after cosmic inflation and reheating, which we will cover later. From last scattering till now, those photons have been traveling the universe and getting redshifted with the expansion of the universe. First, they became redshifted to infrared, so no longer in our visual range. Presently, they are redshifted by a factor of 1090, and their temperature is 2.755 Kelvin. These are the cosmic microwave background, CMB, that we detect as 150 gigahertz microwave radiation today, and which provides strong support for the hot Big Bang model of the universe, and essentially killed the steady state model of the universe from the 1940s and 50s. When our microwave telescopes look at the sky, they are seeing the spherical last scattering surface of photons that have been traveling unimpeded for very nearly the age of the universe to reach our satellites now. An observer in a very distant galaxy will observe his own last scattering surface with the same characteristics. We are at the center of our particular observable universe, but there is no center to the larger universe of which our observable universe is a part. The CMB is the oldest and most distant light or electromagnetic radiation we can ever see. The CMB light predates the formation of stars and galaxies, much older than the starlight the James Webb Space Telescope can see. Much that cosmologists assert about the universe before this time is based on observations of the present universe and models that assume the laws and forces of physics and properties of elementary particles remained unchanged since the early universe. Astronomers would like to be able to detect neutrinos and gravitational waves from the early universe, and they may succeed in coming decades. CMB photons are as common as dirt. There are about 400 million CMB photons for every cubic meter of the universe. The number density of starlight photons is much less. Though our night sky looks black in our visual range, it is bright in this microwave range, brighter than distant galaxies. There is also one helium atom for every 12 hydrogen atoms or ions. The helium atoms recombined before the hydrogen atoms. There is also a lithium atom for every billion or so hydrogen atoms or ions. The lithium atoms recombined fully after the hydrogen atoms, but their density was so low that they did not appreciably scatter the CMB photons. The CMB was emitted almost 13.78 billion years ago. How distant from us are the regions that emitted the CMB light we see? I think most learners like us tend to reply that those regions must be 13.78 billion light years away because that light has been traveling 13.78 billion years. But this is wrong because the universe has been expanding continuously throughout that period. The proper distance from us today is about 45 billion light years, or 13.9 gigaparsecs, and the proper distance at the time of photon emission, last scattering, was 41.5 million light years, or 12.7 megaparsecs, 1,090 times closer. More information about proper distance and the size of our visible universe and observable universe is available in supplemental video number 4. The present radius of our observable universe, a little larger than the visible universe, is 46 billion light years, or 14.2 gigaparsecs. This is the present volume over which neutrinos and gravitational waves from the early universe could potentially reach us. The universe beyond our observable universe could be larger, extremely large, or infinite. We will never have direct information. However, 2 things to keep in mind. First, consider an astronomer cosmologist in a galaxy currently 45 billion light years distant from us. Say this purple galaxy and astronomer. We're here, and the purple galaxy and astronomer is here. They have their own observable universe and visible universe, most of which is beyond our observable universe. So our observable universe is the blue ring, and the purple astronomer's observable universe is the purple ring, and most of their observable universe is beyond ours. They are seeing the CMB originally emitted from our region of space, which we will never see. Secondly, cosmologists assumed that the entire universe that began with our Big Bang was homogeneous and isotropic, not just our particular observable universe. As huge as our observable universe seems to us, it may be an infinitesimal speck in the larger universe, aside from any speculations about a multiverse. Our current observable universe was about 5.6 meters in diameter, 10 to the minus 33 seconds after the Big Bang, or Planck time.